Hello and welcome. Today we are talking about accumulated change, which is week 26 of the math map, and we're going through the complex booklet, although it may not look too different if you are a Challenge B director doing monomials. So the first thing that I always do is some sort of warm up to get the kids thinking about math and trying to get focused onto the logic strand. And so we're still doing quick flip arithmetic, which has been the case for it's the last 10 weeks of the year is all quick flip arithmetic. And the thing that we are, the thing at least that I'm doing in my class for this week is to look at two different things that I think are good to review and good for the kids to have practice on. And the first one is area. So I'm going to say, if I have my tissue box here and I want to get the surface area of just this face, just this one part, how do I calculate that? And hopefully the kids can say, well, area, let me find a marker that I think is going to work. So surface area the equation for it is just going to be length times width. So we're just looking at length times width, and you can flip over a couple cards. You could just pick some random numbers, or you can flip over some cards. So, if I get 2 and 3 on my cards, hopefully they can calculate that real quickly and say that that is equal to 6. So your area is going to be equal to 6, some sort of units. I don't have units, so 6. We'll just calculate it. I'm probably going to have them have their dry erase boards. And so we'll just say, so how are we calculating our area? And then I'll have them write it on their boards and calculate it. Or maybe they can do it in their head. Hopefully, probably most of the time they can do that one in their head. And then I'll say, what if I actually wanted to calculate the volume of this rectangle? Oh, anybody remember what I call this 3D shape? And somebody might say a cube, and I'll say if it's a perfect square, it's a cube. But this is kind of rectangular. It's not quite a perfect square. Do you remember what we call that 3D shape? And maybe I'll have somebody who knows it's called a rectangular prism. And if they don't, I'll remind them because we're still learning a lot of this vocab. So on this rectangular prism, do you know how I calculate the volume for it? And so I will put volume over here. And the volume is it's also going to be length times width, but then we are also considering height or depth. So you can call it whatever you want. You're pretty much just calculating this side, and this side for the depth. So you can call it depth, you can call it height. You'd need the 3 different components, right? So we're going to calculate that. So I'll draw 3 cards. So if I have my 2, and I have my 3, which gives me to 6, and then I have another 2, and so I have 12 is my volume. Okay, and so then maybe just try flipping a few cards, like 2 cards, and say, okay, so what's our surface area? And then flip an extra card and say, what does our volume go up to? And so they're getting some practice of looking at area, and then they're looking at volume and how to do those 2 types of calculations and what the equations are for that. So I think that's a helpful review for them if they haven't been thinking about their geometric shapes and what those are. Plus, it ties in really nicely to the topic today, which we'll talk about area in a different way. Okay, so then my next question is, what if I have this shape? How am I going to calculate the area for this shape? Ooh, I almost dropped this. This is one of our nice pots. We live in New Mexico, and this is from the Acoma Pueblo. So I do not want to drop it. But how do I calculate the shape for something that has curves? And I'll give them a minute to think about it, and we'll see if they have any ideas. Okay, set that gently down. And they might not have any ideas because they haven't necessarily learned about calculating area of curves, right? That's a calculus concept, and they're not at calculus yet. But we're putting them into calculus now, right? Okay, so we would need calculus for curves, and we're going to talk a little bit more about that. And so that's all I'm going to say about that for now, but we are going to come back to that pot in just a minute. Okay, so the next thing that I have them do is I say, open up your booklets and tell me where we are. So they'll open up and go to the math map page where the compass stuff is at, and they can tell us we are in complex, or if you're in challenge B, monomials, and they come down and it is accumulated change, which is still 4D, it's our last week in 4D. And so they should be able to see that and point that out. And then we go ahead and do the exordium, which is looking at the cover page and the front page. So if we look at this, I actually recognized where this was. As soon as I saw it, and I was a little surprised, they would put that in Math Map, and then I realized that they didn't name what the actual location is, that they put columnar, I don't know how you pronounce that word, jointing rocks, photographed by Peter Crutchville. So we are looking at a photograph of all these columned rocks that are a very interesting shape. Yeah, interesting. So if I would say, well, what do you see? And let them talk for a little while. And sometimes they're excited and they talk for a long time. And other days they're exhausted and they're not hardly saying anything. So if I need to get them going, my next question would be, if you had only seen one column in this picture, one little strip of this rock, would you know what you're looking at? Would one tiny little piece really show you what the bigger picture is? And they'd probably say no. They probably wouldn't be able to figure out exactly what they're looking at or be able to guess what the rest of the picture is going to be. Especially the smaller that piece is, the harder it would be to know what the full picture is of what they're looking at. So this picture, or understanding what's in this picture, it really takes the accumulation of all the little parts together in order to give us the bigger picture or the bigger image of what it is. And that's what integration is about. So last week, we talked about how things could be derived from the bigger whole. So I gave the example of pressing down olives and making olive juice, or squeezing a bunch of oranges and putting that down to orange juice. So orange juice is a part of the whole orange, and the olive oil is just a part of the bigger thing of the olive. That was derivation, and that was differential calculus, which we talked about last week. And this week, we are talking about integration, or looking at all those smaller pieces and how that fits together to make the larger whole. That's integration, and that's integral calculus, which is what we're talking about this week. Then I would read the Tolstoy quote, see their thoughts on that, read the reflections, see their thoughts on that, and then ask if there's any other thoughts on how the cover page ties to the concept of an accumulated change, and see if they say anything. Most of the time they don't. Okay, so then the next thing we go to is our I squared page. And so I would say, tell me everything you know before I even pull out the page. Tell me everything you know about area. And we've already kind of refreshed their memory on how they calculate surface area, and then how they look at volume, which is the 3D area. So we've already refreshed their minds by doing that in the warm-up. And so hopefully they can restate, oh, we just did some of this. And so they know that about area. And then the next thing that I want to highlight, so they could say, yes, we did this with the Kleenex box. We showed that example. And then I'll say, yes. And we briefly looked at how we might have a shape that has curves, and there's plenty of curves in the world. Mathematicians have to find a way to calculate for those, and they have. And so I'm going to take part of this curve. I'm actually going to just kind of like break it down so I'm only looking at part of it. I'm going to put it on a graph. So let me draw my graph up here, and I'm actually going to draw it 3 times. And I have a much larger board in my CC community, which is really good because I need a larger board. And then, let's see, I'll just use green because I did that in the picture. So here is my outline of the top part of my pot. So this is kind of like the top part. And if I were to draw the rest of the pot, I would kind of fill up my graph all the way around. But I'm just looking at one section because I like staying in this first little quadrant. I think it's really nice on all these examples, as much as we can, to stay in quadrant 1 for the 7th graders. And then as you get into upper levels of challenge, start thinking about how these other quadrants fill in and fit in. But this is a really easy one to start with for the 7th graders. So if I have my pot, and I'm going to kind of try to draw them all similar. Okay, so that's all meant to be the same image. And I could say, Well, what's one way to calculate the area? If I were just gonna like squint my eyes and blob this and say, what kind of general shape do I know how to calculate that I could make right here? And maybe you'll say, you get somebody who says, well, you kind of have a triangle. If you look at it like this, and you come back here, and you come back this way, you could kind of see a triangle, and you could maybe try to calculate that. What is our area for a triangle? Anybody remember the surface area for a triangle? And they would say 1/2 base times height. So we have our base amount, we have our height amount, and it's pretty much just half of a rectangle. And so that gives us our 1/2 base times height, gives us our surface area, just our surface area of this piece. Okay, that's one way to do it, and it will give us a rough estimate. But if I'm sending astronauts into space and we're going to do, I have certain pieces and I have stuff that's going to take up so much space, do I want general estimates? Am I going to put people's lives on the line with a general idea of how the math works out? Probably not. I probably need something better and stronger than that. So what is another way we could do this? Well, we could kind of break it down into little subsections. So if I kind of look at these as a bunch of rectangles. Okay, those are meant to be generally equal width. I did a really bad job drawing them here, but they're meant to be equal width, generally equal width. So I could look at these, and because I know how to calculate the rectangular area, I can calculate the length times the width, and I can get the general idea of what each of these things total. And then I can do a summation of those. So summation, do you guys remember the symbol for summation? It's sigma, which is it's the Greek letter S, sigma. And then we could say the summation, and we're adding all those things together. And so you would have the summation as, let's say that this goes to the point 2. You would be looking at things from 0 to 2, and then you would have all the stuff that you're adding together. So what's your formula, or what are you adding all together? So you're looking at a summation or a total of those items as you add it together. But if I could go a step further and say, well, I want to look at really, really, really tiny rectangles. Okay, so there's my first tiny rectangle. And another tiny rectangle. And as I'm going over here and I get, so all of these would fill in with, I'd have a bunch of tiny rectangles here. For time, I'm just going to keep going forward. I would have all these tiny rectangles. And because I'm more closely following where there's curves with those tiny little rectangles, I'm getting a much more exact value for that mathematic calculation. So the thinner those columns are for those rectangles, the more accurate my math is. And as I get thinner and thinner and thinner and get closer to 0, I can't go all the way to 0 because then I have nothing. But the closer I get to 0, the closer I get to that limit, the more accurate my math is going to be. And that's what integration is doing. And so integration is shown by that symbol. So that is the integration of something. So the integration is what they use for calculus to try to find that area as close as they can under those curves. Remember I said last week, calculus needs curves. Okay, so now that we've kind of established this and we showed our students this, and hopefully they can understand this, now is the time to actually look at that I2 page. Because I think they could get really lost on this if you don't at least explain how this works and this area stuff works. Okay, so you can compare the function graphs. So the function graphs are shown on here with the black, and then the red lines in this case are the corresponding area graphs. So at the point that this function line has made it to 1, you have one component that is completed of the area. So your line is at 1. And as you move a step over and you get to 2, you have 2 parts that are filled in. So it moves up to 2. You end up with this linear line showing the area of that function. So pretty much I would say for the 7th graders, all they should know is that those red lines are showing the integration, That's what they're graphing on here for them. And just recognize that certain functions have a certain integration line, just like how our certain functions had a derivative line last week. That's all they really should focus on. And if they want to try to see how these, which ones match for what, that's the way to try to approach this and kind of start memorizing. And when we're talking about area, we're just talking about the area that's under the curve to the point that you come to that horizontal axis, the x-axis. So I'm not talking about area that's down underneath here. So we are just talking about the area under the curve to the point that you get to the x-axis. Okay, so that's what I show on the define, how we define area under the curve. Okay, so under what circumstance are these continuous? Well, they're continuous anywhere that the function graph is continuous. So that was the same thing, that concept that we saw last week. And then you don't have it where you end up with like asymptotes and stuff where it's not, the function's not continuous. And so you end up with the integration line not being continuous either. And then how is a function a partial authority? So in all of these cases on this page, we are assuming that our y-intercept is 0. And when you go to the next page, you see the equation for these different integrals, and they're including the y-intercept as a plus c in the equation. And on all of these, you could just add like a little plus c to the bottom of these, but they're just assuming that the y-intercept or the c value is at 0. And that's why they don't list them here. And so you're just looking at these at like the most basic form where your y-intercept is at 0. But you could move those graphs along the line and it still works. It's still okay. You haven't changed anything on the integration. Okay, the next thing, the next page, the I3 page. Okay, so the I3 page, probably ways to approach this is, once again, we are seeing the parent name of the graph that we're looking at, constant, line, radical, rational, all the main ones, right? They should be starting to be familiar with those names because we've said them so many different weeks. They're seeing those graphs. They're probably starting to learn those graphs too. And then over here we have derivative, the function, and then the integral. So last week we talked about the function, and that was the black graph. And then we looked at the derivative, which was the slope of that function. That gave us the derivative. They're listing the derivative again here. So you're just seeing this again. The integral is that area under the curve for the function. And so that's listed all over here for any of those different graphs. So they can start to look at the patterns and start to see the way that they tie together. This C value over here, that's what I was talking about for the y-intercept. So where's your graph starting, where it intercepts to the y-axis. But on the case of the last page, we're always assuming that C value is the y-intercept is at 0. Okay. Oh, the other thing, and this might be confusing, so maybe don't introduce it, and we'll see how my kids respond to this, and maybe I'll take this out of my lesson plans for next year's people. But I thought, and I saw the correlation when looking at derivative, function, and integral, we're kind of looking at three things that tie together. So sometimes you can look at something and look at the inverse. So you could say 1's inverse is -1. You could probably view things as you have this and then the inverse of this would be something else. But when you have three things in the relationship, sometimes I think it can be harder to see how they tie together. But I wanted to remind the kids that we have seen a 3-part relationship where 3 things tie together before. And that was when we talked about base, index, and power. So if you have a base of 2 and your index is 3, then your power becomes 8. So we have base, index, which you put with an n, equals the power. Okay, and then same deal, you could do that, like you could do the third root of 8, and then you get to your base, which is 2, and then you could do this with the log. So the logarithm, and then you have 2, okay, a is going to equal your index, which is 3. So this is the index over the power, gets you to base, And then this one is the log with the base of the power, gets you down to the index. Okay, so in this case, we started with something small, and because we have an index to it, we're bringing it to something bigger, which is your power. And your log is kind of doing the opposite, and it's breaking it down. This one's kind of breaking it down too. And your integration and derivation, differentiation does the same thing. So as you're taking your function and you're integrating, let me make sure I say this correctly. Before I say it, where did I put it? Okay. Yes, okay. So when we go from function and we integrate, which means we're moving over here to the integral, we are increasing dimensions. And Dr. Gilpin said, don't function too much on what that means, because they're probably not going to understand that, but just know that they're increasing dimensions. And then if you were to go at the function, you're differentiating, you're coming back down, you're going from your function down to your derivative, you're decreasing your dimensions or your dimensional understanding. And we get into more in that in high school math, but just know that these are kind of a relationship of how we're building up or we're building down, coming back down. And we kind of talked about that, how integration accumulates all the stuff, but then the derivative is a smaller piece of a bigger whole. Okay, so that is all I had to say about base, power, index. And if that's too confusing to throw that into this lesson, maybe just ignore that. We'll see how that goes. Okay, the charts, key concepts integration is putting together the pieces to see the whole. Okay, and so we did that. We saw that with our area under the curve and how we were pulling together all those tiny pieces. And the smaller the width was on those pieces, the more accurate our number was, the better it worked to actually get our area. Okay. That's pretty much it for the lesson. Okay, so you can run through that stuff, and that's pretty much what the lesson is. Now, when the kids go to do their problems, they have focused, they meaning Lee and Dr. Gilpin and stuff, have focused on the most important information, they would say, is, you know how we normally are doing the tops of the pages? On these ones, it's the column along the right-hand side that says trace the graphs. And so when they divide out into, I divide them into partners or a group of 3 because I have an odd number in my class. So I will just assign them and have them work through and write out what these graphs look like, because we're trying to focus on that. And I think for the purpose of class time, that's the most efficient way to use the class time, instead of trying to have them kind of figure out some of the other stuff. So I'll have them do this. And what's really nice is maybe they'll notice, and if they don't, I'll point out that they actually already did 3 of these graphs last week on their homework assignments, and that we did in class. So they've already seen some of these. They saw the function, they saw the derivative. They actually saw 4 of them, because if there was an inverse, they did the inverse and they might have done a translation. So they actually had 4 of the 5. And then the only additional one is the integral. So they're repeating a lot of the work that they did last week, but these are kind of hard concepts. So it's good for them to just keep repeating that and seeing how those graphs fit together and how the graphs are translated, or the integral of them, or the derivative. So the sooner they can start kind of seeing how those patterns go together, the easier it is to just kind of memorize this information. So there you go. It's not really that bad. It's looking at the graphs and seeing how they tie together. They don't have to understand how everything fits, but I think they can understand, not this, but the integration being that area under the curve, or bringing all of that stuff together to make your bigger picture, and the reason you need integration and why you care about integration. So hopefully that's helpful for you and your students. Good luck.